Hello, everyone. I think we should begin. I got green light from the organizers. I would like to welcome you to today's talk and thank the organizers of this great initiative, REYES, for having me here today. I am Sokratis Trifinopoulos. I am a postdoc at the Center of Theoretical Physics at MIT, and also a member of the Institute of Artificial Intelligence and Fundamental Interactions, or short IFI. So IFI is a collaboration among 4 different institutes: MIT, Harvard, Northeastern, and Tufts University. And I'm thrilled to share with you the work we do there. So first of all, as you might have seen from our logo, we're interested on the fascinating interplay between physics and artificial intelligence. On the one hand, physics has long been the backbone of scientific discovery and has provided us with an understanding of the fundamental laws that govern our universe. And on the other hand, we all observe the remarkable success of modern machine learning in processing large and complex data sets and uncovering intricate correlations between them that would be impossible to do with traditional methods. So IFI aims to enable discoveries in physics by leveraging the next generation of AI technologies. At the same time, there are analytical methods that are devised in the context of physics and can facilitate the understanding of AI themselves. So the basic idea is that artificial intelligence can directly incorporate physics intelligence and domain knowledge. So by infusing AI with physics principles, we can enhance their reliability and efficiency in various industries. But let's begin with physics. And I would like to talk about the smallest scales first that you can imagine. So this world of the very small is investigated in experimental facilities called particle colliders. And here we'll see an animated version of a proton collision event in 2010, which is the year that I'm going to be pausing the video to explain what is happening. So 2010 is the year where the Higgs boson was discovered. And the Large Hadron Collider at CERN is featured, and it is located in Geneva region, actually 100 meters below Geneva region in the borders of Switzerland and France. And it is an underground circular tunnel with 27 kilometers of circumference. And so protons are accelerated to nearly the speed of light, first by the series of smaller rings, which are called the boosters. And then they are injected into the bigger LHC accelerator ring, which is a technological marvel, if you ask me. So this is the ring. And ALICE, LHCb, ATLAS, and CMS are the 4 experiments. That is places where also detectors, particle detectors, are located. So, oops. Yeah. Let's go inside the tunnel now. So the protons race around the ring in opposite directions, and they're guided and controlled by powerful magnetic fields. Here, this is the proton, and you can see the quarks, the constituents of the proton inside. And as they approach each other, they are brought into a collision inside the detector area. This is the detector, into a designated point. This is, yes, so here, this is the point of interest, like the moment of truth. So why we have built all this amazing technology. And this is, yeah, this is where the energy is released from the collision. And this leads to a creation of a multitude of subatomic particles, which arise from the decay, fragmentation of the original colliding beams, protons in the beam, and they're captured and measured by the detector systems. So they surround the collision point. The screen's lights here are the places where the energies basically deposit their, and the particles deposit their energies in the detector. So you can think of detectors as slow motion cameras of the world that are very small, just they collect pictures million times faster than conventional cameras. So for example, a video would be based on 60 pictures per second, while in LHC, when it is operating to its full potential, we have bunches of hundreds of billions of protons crossing each other paths every 25 nanoseconds. And during its crossing, which lasts about 2 nanoseconds, about 50 protons collide and produce new particles. So to capture this event, the equivalent would be 40 million pictures per second, which corresponds roughly to 1,000 terabytes of data per second. So we end up with this vast amount of data that has to be stored and processed in real time. Figuring out which particles came from which collision, as you can imagine, is a very daunting task. So this is where AI can step in and support in order to enhance our understanding of the detected particle interactions. But before explaining this possibility for particle physics, let me zoom out for a moment and make a small excursion to define what we mean by AI and what are the basic tools we rely on. So if you're already familiar with machine learning, this slides would be trivial, but bear with me. So artificial intelligence, in full generality, is the study, the design and study of agents that are able to perceive their environment and are capable of performing tasks which usually typically require a human level of intelligence. Machine learning is the largest and maybe most important subset of AI, and it focuses on developing algorithms that allow the computer to learn from data and improve their performance without any explicit programming. So machine learning algorithms can identify patterns, they can make predictions, and they can uncover insights from complex datasets. The two fundamental types of machine learning approaches is supervised and unsupervised learning. Supervised involves training on a model where the data is labeled, that it means the desired output is provided. So for example, we can take a look at this plot, and the labels here are the colors of the dots, blue and red, and they are provided. So the model learns to distinguish between the two types by forming this decision boundary. So given a new unseen point, it will be able to predict where it belongs and classify it to red and blue, depending on where it lands, on which side of the boundary it lands at. So this approach is useful for tasks such as image and speech recognition or predictive modeling. On the other hand, we have unsupervised learning, and here this involves training on unlabeled data. And so the machine learns to identify patterns and underlying structure by itself. So in this example here, the dots they all have the same color. They are unlabeled. And a famous algorithm, for example, K-means clustering algorithm, uses the notion of geometric distance in order to learn groups that are similar based on this distance. And so it creates its clusters here, indicated with different colors. And this approach is, of course, useful in tasks such as clustering, but also for anomaly detection and in general to explore data and do things like dimensionality reduction. Next, we're going to talk about artificial neural networks. These are the most powerful tools of machine learning when it comes to large data sets. And they come from an idea of the 70s and that is to mimic the basic operations performed by individual biological neurons. So an artificial neuron, which is called perceptron, it receives multiple inputs, applies a specific operation to each of them, and then produces an output, which is based on the collective influence of all the inputs. And so the strength of the ANA lies in its capacity to process and learn from complex non-linear patterns. By utilizing these connections between its components and create layers of perceptrons. And during the learning process, the ANA adjusts the connections, so the synaptic weights between the neurons based on the training data, and it tries to optimize the ability to perform tasks. So these are all mostly examples of supervised machine learning. And it can be actually mathematically proven that the neural network can approximate almost any mathematical function. So we call them universal function approximators. This goes back into this theorem of Horning et al. from 81. And so back to collider experiments. Now you can get an idea of what AI can do to help us. So physicists can use AI that have already been designed for example, in image recognition. Convolution neural networks are one of the most important architectures. And so we can use them in order to distinguish between particles. So we train the machine to understand what a Higgs boson or what a Z boson looks like, and make a decision of what is what out of the raw data collected, as we explained before in the collider experiment. So this pipeline, starting with first with a marvelous engineering miracle of accelerators and colliders, then with a collection of raw data by experimental physicists, and then the analysis supported by AI. And finally, theorists come up with a few lines of equations. Well, in this case, this is the expanded form of the Lagrangian of the standard model of particle physics, so it's a little bit longer, but still, this is an elegant description of such a complicated underlying phenomenon, and this is, to me, one of the most mind-blowing aspects of modern science. Now let us switch gear and look into the world of the very large. So we leave the subatomic world and go to the cosmic scales, where we're interested in macroscopic and supermassive objects such as planets, stars, black holes, or clusters of these objects like galaxies. So in this example, which comes from research done in IFI, we are interested in the questions of how galaxies come about. Let me play here another simulation. So it is thought that galaxies form through mergers. And this is a quite cannibalistic process. So collisions of smaller galaxies lead to larger and larger ones. And notice that each of these galaxies have their own dark matter halo around them. So by observing the visible light coming from the stars in them, we can make a connection to dark matter and possibly explain its nature. So what we would like to do is to build this merger tree. We can think of it as a family tree. And let's study our own Milky Way, for example. And so time flows from the top, the diagram, to the bottom. And so we would put the Milky Way at the bottom here, and we want to fill the tree with its ancestors, starting from the closest relatives all the way to the ones in the top, which are the oldest ones. So we have large Magellanic Clouds and Sagittarius here, and the progenitor is Gaia and Enceladus. But we will also like to know what else has happened. And so how are we tackle this problem? So we're faced with a classification problem. What we want to solve is we want to identify which of the stars in our neighborhood is coming out of a merger event. And it turns out in our solar neighborhood, that will be only 1% of the local stars. So it is the definition of a needle in a haystack problem, in which case we are really taking advantage of using a neural network to do this job for us. What we can do is we can use a simulated galaxy where we know what is happening and train on it, and then ask the same question in real data. So this is a picture of a simulated and a real galaxy. Can you tell what is what? So yeah, the one on the top is the simulated one. It looks fantastic. And so the whole process is to teach the computer which stars are immigrant stars based on the simulations. Then we can apply it to the real data. And so we mentioned the simulations are extremely important besides classification. And this is another topic that AI can do fantastic job. Realistic physical simulations are more tractable than ever. So in this video, you can see a simulation generated by graph neural networks, GNNs. And it presents physical systems with particles, which are expressed as nodes in a graph, and information is propagated between the nodes. So it can learn to simulate a wide variety of very challenging physical domains involving fluids, rigid objects, deformable materials. It is truly remarkable. And on the other hand, this is an example of another simulation where we've done conclusions that we were not expecting. So this is really one of these examples where the researchers were impressed by that. They did not even believe that the results are true. So the leading researchers said that I thought it was a student's mistake. It was a little bit hard for me to believe. So what is happening is that they simulated, this comes from the Camels project, and they simulated galaxies, and they found that the machine learning algorithm can predict the overall makeup of the digital universe just by examining single galaxies. So it's fit analogous to analyzing a random grain of sand and make conclusions about the whole mass of Asia. So it is a pattern that maybe someday we understand, and astronomers would be able to make conclusions about real cosmos just by studying its elementary building blocks, in this case, galaxies. So this is a recurring theme in physics. Next, we move to language models, which are becoming more and more popular nowadays. This is models that have been trained on massive amount of textual data, and enabling them to understand like text input from humans and generate human-like text themselves. And this is an impressive capability, which it can also extend beyond language-related tasks. So, for example, here we see Google's Minerva, which can solve for you high school or even undergrads math and physics problems. This is a state-of-the-art math-specific model. But yeah, of course, it is not perfect. It will do some mistakes from simple arithmetic to getting the fundamental reasoning wrong. However, we're just at the dawn of AI, and these models are already quite impressive. So Minerva gets 60% of the STEM questions correctly, and ChatGPT 4, which is not even math specific, can do even better. So it is important also to check that it is not only memorization, and that you can do by a validation step that you can do is to present novel math problems to the AI. And it has been shown that it is not only memorization, because they can also handle these problems. Well, the bottom line is that there's still work to be done in all fronts. And for those of you that are present or future machine learning practitioners, you should be excited about architectures like this one here. This is a transformer, which is the secret sauce behind the success of the large language models. And you can find this article here. It's quite recent. Well, machine learning is not recent anymore because the field is advancing so fast. But this is where the transformer architecture was first discussed. In iFi, we have our own version of ChatGPT. This is ChatGPT, where a virtual physicist will give you the answers that you're looking for. So please go ahead and try ChatGPT. Jesse Taylor being the director of the institute, by the way. And so we have all this massive development. So we have ChatGPT, we have stable diffusion, companies spending billions of money on these impressive models. The question is, can we leverage them for scientific data and analysis? And the answer is yes. So this is a slide from my own research at iFi. We got inspired by these language models and built an architecture that does multitasking over many questions, like not in various fields of science, but in particular in nuclear physics. Yeah, it would be an ambitious goal to build an AI for whole science, but in nuclear physics, it can make world-leading predictions about the various properties of the nucleus. The nucleus, I remind you, is the center of all atoms. It is composed of protons and neutrons. And properties would include the binding energy of the constituents inside the nucleus, the radius, the various half-time decay rates, the many observables which are macroscopic. And due to the complexity of the strong nuclear force, it is nearly impossible to calculate these observables from first principles. So we have used this particular machine learning architecture. We call it NuCLR, nuclear. And by training on all of the different quantities, we enhance the performance of the network in order to achieve this accurate predictions. Here's a heat map of the binding energies, the difference of the model predictions with the measured values for the binding energies. In the two-dimensional plane, here's the proton number and the neutron number. And so the agreement is really state-of-the-art, establishes a new state-of-the-art. So yes, multitasking and moving towards general purpose AI in this sense is one of the avenues. But also we are interested in the interpretability of our models. And so this is an example where we can use tools designed for physics in order to invert the situation and use them to understand the AI themselves. So how that could be done? An example is symbolic regression. So symbolic regression is a method, is an algorithm that generates population of candidates of equations. And then it uses again a method like a technique inspired by biology, genetic programming, and in particular inspired by biological evolution and the survival of the fittest, to iteratively refine the population of these equations and converge towards the most accurate ones that can describe the data. And so you have learned Newton's law of gravity in school, and AI can do that as well. Here you can see that the highest score is the one with the correct equation, the highest score of the symbolic regression software. And now the idea is to use this the software. This is Pyser, which you can find in this link, and come up with simplified equations to describe the model itself. So, for example, UCLR, and gain some. It's not going to be exact, but we can gain some analytical understanding of what has happened to the AI during training. What is the how we can express the latent representation space with symbolic expressions. Another example of what one can do in order to exploit physics domain knowledge to understand the AI is to make this connection between neural networks and thermodynamics. So in particular, we can use statistical field theory, which is a theory developed to describe complex systems and the emergence of collective phenomena, such as magnetism or superconductivity. It is a bridge between the microscopic world and the macroscopic world. And in the same spirit, we can treat phenomena such as learning or memory formation as emergent behavior out of the many interactions that exist between the different neurons. And so understanding the dynamics of AI will help us to optimize their performance and also their generalization abilities, and also make them more robust to noise. So to sum up, we want to get people excited about IFI's activities and research. So we talk to school students, teachers, general public. For example, at the Boston Science Festival, we talked to more than 100 students and teachers. We organize many different events, mostly in the Boston area. So if you're around, please reach out to us and connect. We'll be excited about that. Thank you very much. So that is the presentation, and let me take the Q&A session. So the first question is, if you were to use convolution networks for particle identification, what would the input data be? So the input data would be really the raw data from the detector. So you can think about the data as point clouds. So you have the position of in the detector where the particle was detected, and also as weight you have the energy of the particle or the transverse momentum. And then there are many different techniques from neural networks, from convolutional neural networks to unsupervised clustering algorithms in order to connect the theory and what we know in theory. I hope that answers the question how the data looks like. Then we have another one. Can AI help us discover the origin of the universe and help us understand how was life on Earth and other galaxies originated? Wow, this is a big one. So the origin of the universe is within the realm of physics if we have the Big Bang in mind. And as we have discussed in this presentation, the laws of the universe, the ones govern the very, very small scales and the ones that govern the very, very big scales, they are described by physics, and AI I brought you a lot of examples about how AI can actually facilitate our understanding. And the really mind-blowing fact is that the world of the very small and the world of the very large, due to the fact that the whole universe had the size of a subatomic particle in the very beginning, they are connected. So there is a mind-blowing connection between particle physics and cosmology. And everything, the physical laws that you postulate and in particle physics, they have to be consistent with observations that we take out of the cosmos. So yes, as far as physics is concerned, I would say that AI is extremely helpful to make us understand even better what is going on. And well, I also brought you an example where AI has taught us something about the composition of galaxies and the connection to the composition of the whole cosmos that we didn't know. We might not be able to appreciate it fully and understand it fully at this point, but if it is not just a feature of data and its uncertainties, but there's some hidden underlying reality to it, then this is one of the most exciting prospects in this industry of combining both. Now, about life on Earth, this is a question about biology. And I'm definitely not an expert to talk on this, but I know for a fact that AI is of extreme importance also in the field of biology. Then a question about how to expect synergic relationship between physics and AI to change over the following decade. So it depends on the field. Definitely when it comes to particle physics and collider physics in particular, this the study of how to go from the detection of particles to the models like quantum chromodynamics and all the theories that the standard model of particle physics is based on. In that respect, AI research is basically taking over all traditional methods. In other fields of science, against in other fields of subfields of physics, I would say the more theoretical the discipline, the more important it is to find explainable, interpretable AI. So that is what we are striving for in this particular new CLR example. This is going to be a theoretical model, making theoretical predictions. And so for the theories to be on board, we need to convince them that the basic concern here is that neural networks are black box. So we don't exactly understand what's going on. We feed them with input, we get some output. So having methods such as representational learning, when you can look at the underlying patterns that emerge from there in the low dimensional representation space, or using symbolic regression and similar tools to explain what your network has learned, is of utmost importance if we are to see AI taking over also theoretical disciplines. But for experimental analysis, collider physics or astronomy, for example, astrophysics, and there we have also an immense amount of input from the various experiments. For example, also in the study of gravitational waves, like we're talking about billions of terabytes of data that have to be analyzed. So machine learning is definitely the way to go. I don't see any other questions for now. So I think we have already answered those. I hope it's included in the recording because I forgot to click on recording the answer. But I think the video is going to be uploaded, so I suppose it should be included. Okay, so if there are no further questions, thank you very much for your attention. And yeah, I'm hoping that in the future, some of you might be interested in IFI and would even apply for a fellowship for a PhD or a postdoc in the future. Thank you all.